Hello everyone, welcome back to MP Coding. Today, we're continuing our series on synchronization primitives in FreeRTOS. And in this video, we'll be talking about stream buffers. In the previous videos of this series, we've already discussed several types of synchronization primitives in FreeRTOS. If you're new here, I recommend checking out those videos first. They'll give you a better foundation for today's topic. So, in today's video, we'll explore stream buffers. A one-way communication channel designed for continuous streams of bytes. They are typically used for sending data from an interrupt to a task, for example, when receiving data from UART. You can think of a stream buffer as a circular buffer that's automatically managed by FreeRTOS. Alright, let's look at the example. I have opened STM32 Cube IDE. And just like in the previous video, I'm using the STM32 F429i discovery board. First, I set up the system clock to use the external crystal and configure the high-speed clock to run at the maximum frequency of 180 MHz. Next, under the middleware section, I enabled FreeRTOS using the CM-sys v1 wrapper. I kept all the FreeRTOS configuration parameters at their default values. Then, I configured USART1 just like before, and enabled the USART interrupt. The MVIC priority for the UART interrupt is set to 5. As in previous videos, I've connected the relevant GPIO pins to a logic analyzer so we can observe the signal activity during the demo. I also switched the timer source to a dedicated hardware timer instead of using the default system tick. These setup steps were already covered in detail in earlier videos, so I'll skip over them quickly here. Alright, with everything configured, let's go ahead and generate the code. In this example, I'm not using the CM-sys layer. So, I have removed the CM-sys include and only added the essential headers needed for this demo. For this example, we need to include the stream_buffer.h header along with FreeRTOS.h and task.h. I've also included string.h to use the some string related functions. I've already written the code, so let's take a look at it. At the top, I created a stream buffer handle variable and 2 task handles. One for the producer and one for the consumer. Next, I defined 2 macros. Stream buffer size set to 64, and trigger level set to 1. I'll explain what these mean in a moment. Here, you can see the task functions defined below. Inside the main function, I created the stream buffer using xStreamBufferCreate, passing in those 2 macros. Stream buffer size and trigger level. Let's break down what these parameters mean. If we open the stream_buffer.h file, we can see the list of available functions related to stream buffers. When we create a stream buffer, this function allocates memory dynamically and returns a handle. If you want to use static memory instead, you can use xStreamBufferCreateStatic. In this example, I'll keep it simple and show the case using dynamic memory allocation. The first parameter, stream buffer size, defines the total capacity of the stream buffer, in bytes. The second parameter, trigger level, defines the minimum number of bytes that must be available in the buffer before a task waiting to read is unblocked. So, what does trigger level bytes actually do? When a receiving task calls a read function, it might have to wait until some data becomes available. The task remains blocked until at least the trigger level number of bytes is present in the buffer. Once the buffer has that much data, or if it becomes full, or the timeout expires, the task is unblocked and allowed to read. In short, the trigger level defines the wake-up threshold for readers waiting for incoming data. And remember, the trigger level must be less than or equal to the buffer size. If you don't need a specific threshold, simply set the trigger level to 1 byte, so the reader wakes up as soon as any data arrives. Now, let's go back to the main function. After creating the stream buffer, we first check whether it was created successfully. If it is, we print a confirmation message to the console. Then, I created 2 tasks, the producer and the consumer, both running at the same priority. I've already explained the parameters of the xTaskCreate function several times in previous examples, so I won't go through each parameter again here. Finally, we start the scheduler. Now, let's look at the task functions. In the producer task, I first created a character pointer and assigned the string, hello from producer. Inside the infinite loop, before transmitting data to the stream buffer, I send a message through UART. This helps us identify when the producer is actively sending data. The function xStreamBufferSend is used to send data to the stream buffer. We need to pass these parameters. The stream buffer handle. A pointer to the data that needs to be copied into the buffer. The length of the data to copy, and the maximum wait time if there's not enough space available. This function returns the number of bytes actually sent. if the number of bytes sent is not equal to the total length of the transmit data. We print a message through UART saying that not all bytes were successfully sent. If all bytes are successfully written, we toggle the GPIO pin PG13. So we can observe the signal using the logic analyzer. Finally, the task waits for 1 second before repeating the process. Now, let's look at the consumer task. Here, I created a character array RX buffer to store the received data. Inside the infinite loop, the function xStreamBufferReceive is called. This function waits for incoming data from the producer. The parameters are the stream buffer handle, a pointer to the buffer where the received data will be stored, the size of that buffer, and the maximum wait time, in this case, set to port max delay, meaning the task will wait indefinitely until data becomes available. If bytes received is greater than 0, the consumer toggles GPIO pin PG14 to indicate a successful receive event. Then, it transmits the received data back over UART, so we can see the result on the console. Okay, let's flash the code to the board. As before, I've opened the logic analyzer and the serial console so we can observe the output in real time. Now, let's continue. You can see both the UART output and the logic analyzer signals. Immediately after the producer task sends data to the stream buffer, the consumer task reads that new data from the buffer. This clearly shows that the stream buffer send and receive operations are working perfectly. Okay, let's change the trigger level now. As I mentioned earlier, the trigger level is the minimum number of bytes that must be available in the buffer before a task that's blocked on reading gets unblocked. If we look at this TX data, it's exactly 21 bytes long. So, I'm going to set the trigger level to 42 bytes. That means the producer task will need to send data twice before the consumer task wakes up to read from the stream buffer. Let's check it in action. Here in the logic analyzer, you can see that the consumer task waits for 2 cycles of the producer task, meaning it's waiting until the buffer reaches the trigger level bytes before it starts reading. That part is fine. We can understand what's happening. But there's something interesting here. You can see that the PG14 pin, which represents the consumer task, toggles twice immediately. It looks like the consumer is receiving data 2 times in quick succession. Why is that happening? If you remember, the consumer task's receive buffer is only 32 bytes, but our trigger level is set to 42 bytes. That means the consumer can't read all the data at once. It reads part of it, and the remaining data triggers another receive right after. Let's fix that by increasing the receive buffer size to 50 bytes and run it again. Now, you can see that the PG14 pin no longer toggles twice, it only toggles once. That means the consumer task now has enough space to receive all the data in one go. Now let's look at copying data into a stream buffer from an ISR. For this demo I changed the trigger level back to 1, and declared a 1-byte UART receive variable. This example only has the consumer task, there is no producer task. In main I create the consumer task and start UART reception in interrupt mode. Inside the UART ISR, I'm not reading a full string from the UART peripheral. Instead, when the ISR receives the character R, it copies a fixed message into the stream buffer. If you want to send the actual message received from the UART, you can increase the receive buffer size and then copy the UART RX buffer into the stream buffer instead. We call the ISR safe API xStreamBufferSend from ISR to copy data into the stream buffer. This function takes 4 parameters. The stream buffer handle, a pointer to the data to copy, the number of bytes to copy, and a pointer to a base type variable, x higher priority task woken, which the function sets to PD true if calling this function unblocks a higher priority task. Returns the number of bytes actually sent. In production code it's a good idea to check that return value and handle partial writes or failures, for example, log a warning or attempt to resend later from a task. The message MSG is stored in read-only memory, so the pointer remains valid. If you instead send pointers to stack memory, you'd get dangling pointers. Avoid doing that. Right after the send call we toggle PG14. That gives us a visible indicator on the logic analyzer that the ISR has run and attempted to send data into the buffer. Finally, we restart UART reception, so the UART will generate another receive interrupt for the next incoming byte. Okay, let's check this in action. You can see that when I send the character R over UART, it triggers both PG14 and PG13. This means the consumer task successfully received the message sent from the ISR and printed it correctly. That's how we can use an interrupt service routine to send data to a stream buffer in FreeRTOS. This method allows efficient communication between an interrupt and a task. The ISR pushes data into the buffer, and the consumer task receives and processes it asynchronously. That's all for today. Today we learned how both tasks and interrupt service routines can send data to a stream buffer in FreeRTOS. The consumer task received the data correctly and printed it, showing how stream buffers help in smooth data transfer between tasks and interrupts. In the next video, we'll discuss message buffers, another type of synchronization primitive in FreeRTOS. So stay tuned, and don't forget to like, subscribe, and share. Thank you for watching, and see you in the next video.